The Luma said, okay, Kimi-K2. Last week we went over the original Muon paper. So basically, the really cool thing, if anyone has seen it or trained models, is figure three. They have a very, very smooth loss curve. Normally, when you train, there's big spikes. Big spikes are not good because you have to kind of like intervene, see like, okay, is the model kind of cooked? Do we have to roll back? Do we have to go to a new checkpoint? Do we have to fix stuff? That's like kind of where you have to stop your training and like your GPU utilization gets kind of cooked. What they did is they have a new optimizer that gives us really, really smooth loss curves with like no spikes throughout the entire training process. This is kind of crazy. Um, I won't go super into detail on the optimizer since last week we basically covered it. So I think the recording is already up on YouTube. If you're interested, watch it. But okay, Kimi-K2, who's used it, who's heard of it, who doesn't know what it is? If anyone wants, to just interrupt me whenever and we can answer questions. So basically, this is like state-of-the-art open source model. It's very, very big. Um, I'm gonna check chat real quick. Okay, nothing about this. So basically, this is a trillion parameters. It's not a thinking model, but it's like DeepSeek V2 moment, like the second DeepSeek moment. What they did is basically it's like better than Claude on all coding benchmarks, better than like anything. It's very, very state of the art. It's not thinking, and it's a very good non-reasoning model. It's very open source. They shared this optimizer that's basically like a better Atom W. And this week we just got out the actual tech report paper. It's decent, honestly. It's like the first highlight of once again, how do you train a very, very large model? So it's like kind of a pre-training, post-training, how do you train a large model? And then the interesting note here for me was you get to see the problems of using China chips. Like they have the H800s, right? Because there was an export restriction. So these chips are like different than interconnected nodes. And what do they do to come around that? I think like 2 weeks ago we covered the other reasoning paper, Magistral, the reasoning paper from Mistral, and they show how they can just like skip some of these issues for full GPU efficiency. But yeah, here's Kimi K2. So trillion parameter, huge trillion parameter model with 32 billion active parameters. Very, very sparse. They talk about the sparsity. They talk about like experiments they did for sparseness ratios and all this stuff. It's pre-trained on 15 trillion tokens. They use a muon clip optimizer. This is basically like all the hot news. They put out a separate paper about this before. What this basically leads to is very, very good training stability. So they have this QK clip technique where they're kind of clipping attention gradients, and yeah, it's just very smooth training. Okay, so trained on 15 trillion tokens, trillion total parameters, 32 billion active parameters, very sparse. And then the big thing here is zero loss spikes, which is kind of crazy. During post training, there's multi-stage process. They do a lot of synthetic data work. Another fun thing I would recommend about this paper for people is they do good citations into other work. So if you're interested in different like synthetic data generation pipelines, they cite quite a few cool papers. There's a few in there that are like good citations that I'm gonna follow up and read. Estimates on the compute used in training this. Yeah, I think they actually say how much compute they used, how much training compute, how many GPUs and stuff they had. No, it doesn't. That doesn't account for a lot of the experiments. They have a lot of like aberrations and stuff. They have a lot of data generation. I don't know if that necessarily ties into how much they used for it, right? They share a decent amount of numbers, but they don't share everything. Um, yeah, so large synthetic data synthesis pipeline and a joint RL stage. Honestly, I found this model a little confusing because everyone calls it not a reasoning model. And like, sure, it's not reasoning per se, where it's like GRPO, like rollouts, just like proper RL to think. But they do have a lot of like RL to think. So I don't know where the line blurs. And I think this is a discussion we can have later. And I'd love to hear people's thoughts. But like, I would semi call this a reasoning model. Like it reasons and it's trained to reason with a like similar GRPO with some changes. But yeah, it's state of the art, very, very good coding model. You can plug it into Cloud Code and stuff. Three bench verified 65.8. It's like right up there with Opus, O3, all that stuff. And it's very sparse, you know, it's sparse. It should be cheap for people that host it for inference. On everything else, it's pretty good. It's very open source. They give base model and post-train checkpoints. It's nice. They do base model evals as well. What's the difference between a reasoning and a thinking model? Yeah, that's a good question. Mostly we don't call stuff thinking models. We just have reasoning models and non-reasoning models. In this case, I would consider this thing to be like a reasoning model. But yeah, I guess there's just think tokens. They just take out the think tokens and they just let it kind of reason. Um, Performance pretty good. I think we can cover charts later. Let's just get through the paper for now. But if anyone's interested in diving on any of these, we can kind of look at it. Um, but yeah, you know, like coding benchmark, basically up there with Opus. The one that just beat this recently. So like the cool thing with this paper is it beats DeepSeek in like across the board on everything. Um, as of a week later, Quen Coder beats this at coding, which is cool. So, you know, stuff is moving fast. They basically reran a bunch of benchmarks except for Opus. Opus, they just took their numbers. I think Open Hands helped them once we bench verified, so shout out to them at the end. But Opus was expensive to benchmark. It's crazy how expensive benchmarking is. So, but good for them to do it. Basically, in the introduction, they go a little like you know, broader and they want to explain what are these terms. So they have this like vision of agentic intelligence, right? Models are no longer static, like they don't just do next token prediction. They need to be agents, so they need to like evolve from static understanding of what they know, and they need to be able to plan, reason, act in environments, use tools and stuff. So a lot of what they want to do, and like, you know, dynamically adapt to these environments. So what they basically want to do is they want to train a model that's really, really good at tool use. So um, they train it on a lot of like environments, agentic tool use. They generate a lot of these tools, and they want it to acquire skills beyond training distribution and adapt behavior through experiences. So like this is kind of like the motivation for why this exists. You know, this thing should be able to pick up tools really good. And like when I mentioned there's good citations of papers for like synthetic data gen, they also have stuff that's like, here's what we were influenced by in tool use papers. Here's like four papers that do really good tool use, and here's how we build upon that. So, you know, if you're interested in tool use stuff, you should probably read the other four papers. Okay, achieving agentic intelligence introduces challenges in both pre-training and post-training. Um, Pre-training must endow models with general purpose priors and effective token efficiency, learning per signal. Post-training must transform those priors into actionable behaviors. Yet agentic capabilities such as multi-step reasoning, long-term planning, and tool use are rare in natural data and costly to scale. So what this is saying is basically you need a decent enough base model to do all this stuff. And for post training, like this data is not really existent and it's like hard to scale, right? So like we don't really just have a lot of multi-step reasoning, long-term planning, tool use data. So you know, they do a lot of scalable synthetic data gen. Okay, paper model, big model, trillion parameter MOE with 32 billion active parameters. There's few major things here. Muon Clip, which is their new novel optimizer. It's basically better than Atom W. This was introduced like quite a while ago, but it was trained at small scale and it wasn't really scaling very well. So in this paper, they show scaling up this optimizer and sort of having gradient issues in attention. So the way they solve it is this kind of stability enhancing QK clip, where they're clipping off a lot of attention a lot of attention weights. So from there, it's kind of crazy. They don't have a single loss spike. Very, very beautiful training curve. Okay, then they have a lot of stuff on their data gen. So large scale agentic data synthesis pipeline. I thought this was like kind of basic. I'm surprised how much it just works, but pretty cool stuff on synthetic data gen. Basically, they generate a lot of tools, tool demonstrations, tool descriptions, and then they have environments for it to use this stuff. And they have like verifiers and in the middle step verifiers, but it's like a cool pipeline that they use for all this data gen.
Why
Then
did you think it was basic?
I mean
Right?
we'll go into how it is later and how it's evaluated. Um, I thought it's like the verification of some of this stuff isn't that crazy, you know?
Yeah,
And
it's
like
Rubik base. Yeah.
yeah, it's a lot of rubric based. I'm surprised it just kind of works, you know?
Okay, that makes sense to
Especially
me.
at the scale and like how they achieve diversity. Like from the techniques they explain, I wouldn't expect the amount of diversity that makes this actually work out. But
Yeah.
we'll dive into it in a bit, you know.
Yeah, a consistent question I had for folks is that how do you evaluate on non-verifiable reward? Like essentially things that are not code or software, and everyone's just saying Rubik base would work. And I think this is an example of, hey, Rubik base actually does work. So
Yeah,
I'm surprised that that's all you need.
they talk about this specifically. So for stuff like creative writing and stuff, they they share how they generate this pipeline. Is it true they used MCP tool architecture outputs? Yeah, they basically have a whole bunch of MCP stuff. So they scrape like 1,000 MCP tools and then they generated even more. So MCP is all you need in this. We'll get into it later. And like actually they have a scatter plot of different tools. Um, see, T-SNE visualization of real MCP tools. Colored by their original sources. So thousands of MCP tools. Of course, they have crypto bullshit, but you know, this is their MCP tools. Then they have synthetic tools, which are also, in different domains. I love how they just have an unknown domain, but they have crypto bullshit where it's some of the MCP tools. But that's part of it. Okay, okay. Continuing on. Where were we? Okay, they also talk about their RL framework. It's RL with verifiable rewards. This is what Eugene was talking about. It's not just code and math. They have it on like general domain, so like creative writing and stuff. Okay, so kind of interesting. They talk a lot about critiquing outputs instead of like GRPO where you do rollouts and reward the best output. They just have a lot of critiquing here, which is kind of interesting. I found their explanation of how they set up this whole loop to be a little confusing. So like their training loop, it's a little odd, but I don't know. Maybe someone else had a better intuition while reading it or broke it down or looked into it more. But they do share a lot about that. Okay, pre-training, 15 trillion tokens. They talk a lot about token efficiency and how it's important. Basically, RL is very token efficient, right? So guess what? Do RL. Um, they talk about pre-training techniques. So effectively, this muon optimizer, it's very, very much a token efficiency thing as well. Then they have synthetic data gen. Of course, their ultra sparse MOE is efficient. It's MLA, so multi-head latent attention, which was derived from DeepSeek. And then they make some modifications. They actually show scaling laws for how sparse you want MOEs. There's charts of this later. Muon clip. So this is the optimizer and what they do. I was thinking we actually just skip this for now since we basically did this last week. But if there's time, I think we come back. Let's see if there's anything basic to say about it. So, outperforms Atom W, better token efficiency, um, leads to training stability, constraint attention logits. So attention was having issues. We constrain it, apply kipping to unshared attention nets. Yeah, I think we go over this later. Let's just go through the paper first. Unless anyone wants to ask a specific question, or Eugene, do you want to say anything about it? Okay, let's just move on since we basically did it. So if you're interested, We'll either cover it at the end or check last week's thing. Okay, pre-training data, improving token utility with rephrasing. It's interesting how much they just did rephrasing. Like they show cool little experiments here of rephrasing versus repeating for multiple epochs and how their strategy is kind of better. So token efficiency refers to how much performance improvement you can get out of each token consumed during training. Increasing token utility, the effective learning signal for each token contributes, is pretty important, right? So that's something that they want to focus on. Naive approach is basically just do more epochs, right? Eugene, question, comment. You're muted.
Oh, sorry, not a question. I think you briefly glanced at the table. We will go through it when we go through the table. I think the table is absolutely insane, where the delta between the second row and the first row essentially almost answers all of the gain. But we can talk about it when we get here.
Yeah, it's interesting. Um, so basically, like you guys know what multiple epochs are, right? So you take your, let's say you have 1,000 samples, you train for 10 epochs, you train on the same data 10 times. Um, so that's one naive approach. Another, so they compare to that. You do get some gains from doing multiple epochs, and it's somewhat common for some data. Like for your base pre-train, we don't do multiple epochs anymore. We used to. For some higher quality data, like some high quality reasoning, we'll do it for multiple epochs and do the same data multiple times. But here's kind of what they do. A key advancement is synthetic data gen to increase token utility. So they have this cool rephrasing pipeline. Basically, instead of just train on the same data multiple times, let's kind of rephrase it a little bit. There's two domain specialized rephrasing techniques that they use for knowledge and math. So knowledge data rephrasing. A single epoch is insufficient for comprehensive knowledge absorption, while multi-epoch repetition yields diminishing returns in the risk of and increases the risk of overfitting. So we'll get to a chart in a bit, but let's talk about what they do. So first is style and perspective diverse reprompting. So prompting guide is you take an LLM to generate faithful rephrasing of the original text in various styles from different perspectives. Then there's chunk-wise autoregressive generation. Basically, if stuff is very long, just do it in chunks. So rephrase segment by segment, then adopt autoregressive like chunking fixer. So divide text into segments, rephrase them individually, stitch them back together, and fix that. There's like a little pipeline on. There's a little diagram on this later. Um, to ensure consistency between original and rewritten content, there's fidelity checks that compare the semantic alignment of the rephrased page with its source. Yeah, cool. So basically, they do all this, then they run a little experiment. So let's compare how this performs in the sense of token efficiency. So there's three things that they do. One is you take your original data set, you train on it for 10 epochs. Risks here are, you might overfit your data. So you might overfit and it might just, you're not really adding more quality. You're just doing the same thing multiple times. Two is rephrase the data once and repeat it for 10 epochs. So basically, you take all your data, rephrase it in a different sense, and then you train for 10 epochs. Three is rephrase the data 10 times with a single pass of training. And here's kind of the results. We extend this method towards larger stuff, and each corpa is rephrased at most twice. So 10 epochs on same data, they test it on simple QA, they get 23. Just rephrasing it once and training it for rephrasing it once and training it for 10 epochs gets you quite a bit of improvement. Then there's rephrasing it 10 times and doing one epoch. You still get a little bit more improvement, but the main difference, like Eugene said, is just here. Rephrasing makes quite a difference.
Am I
Eugene, you
reading
wanna
this right? When actually the first row and second row, each of them are 10 epochs, but the difference between the second from the first row is essentially the second row actually does data cleanup by rephrasing it.
it's not data cleanup, it's data augmentation. So I think they keep both the original data and rephrase it.
Oh, I see. So they keep both. Okay, I was reading it
Mm.
wrong. I thought the first one was raw, 10 epochs. Second one is only rephrased, 10 epochs. Um,
You could be right here. I
yeah,
read
because
it
I'm
as
yeah.
I read it. So what Eugene is saying is, in the the benefit just comes from rephrasing. What I read this
Exactly.
as
Yeah.
is keeping the original and rephrasing it.
I think I'm right because if you look at the paragraph, it says rephrasing the data once, repeating it, which I think as it as the rephrase data. If you look at the third line, which is so that essentially cleaning up the data to be better. That's all the juice. So that's pretty mind blowing to me that someone they did this ablation. So that's really nice.
Yeah, beautiful
That,
little ablation. Basically rephrasing, you get so much data quality improvement. But the reason I interpret it the way that I did is because um, you know, I thought that 10 epochs of the same data is basically just the same data. Adding in another look and doing it for 10 epochs gets you better performance. But I think we'll dig into it later. Somewhere at the bottom, they have a lot of this in the appendix. I wouldn't be surprised if they talk more about it. We'll have to check. Um, this is their kind of chunking for long context diagram. Basically, chunk it, rewrite, and then merge it and check. But nothing crazy there. Uh,
I had a question on this actually, this diagram. Um, I'm taking a lot of time, but uh, in the third column, let's say we rephrase partial input one. What does it mean to be autoregressive?
Oh, like you're adding in the first chunk and the second chunk. Like you're using the first chunk to write the second chunk, I think. So here, chunk-based autoregressive strategy. Texts are divided into segments, rephrased individually, then stitched back together to form complete passages. This method mitigates implicit output length limitations. The autoregressive part, I think, is, let's see,
So when I
chunks.
read the paragraph, I read it as okay, we split in the paragraphs, we rephrase it, and we just smash it back together. But I realized that the first few phrases makes a lot of difference to maintain global coherence. I think
Yeah.
what they're doing here is they're rephrasing the first paragraph, add the first paragraph and the second paragraph, add the new first paragraph and the raw second paragraph, and ask it to rewrite the second paragraph. And I think by doing this, it keeps the style of the first paragraph. But I want to make sure if I'm understanding this right.
That's how I'm interpreting it too. The input is split into smaller chunks with preserved context, rewritten sequentially, then concatenated into a fully rewritten. But it could be the other way too, which wouldn't be as good.
If it's the
Um,
other way, then it doesn't have to be sequential, right?
yeah.
If you just do everything, it can just be parallel. The fact that it's
And,
I yeah. Anyone
and also
else?
the graph
Oh, go
also
ahead.
shows they are feeding the previous segment into the rewrite step. So like the second rewrite model has like two inputs. It has the like original segment and then also the rewritten previous segment.
I
So I
think so.
think
So
yeah,
let's
they're
say if we are
using
rewriting the last chunk, do we pass in everything or do we just need to pass in the last chunk minus one?
in this,
I,
it's just last minus one, right? You can see in the
yeah, it looks
diagram.
like partial except two, right? Yeah. So okay,
Yeah,
I think that's good.
one's not going into three, but one is kind of already seen.
This is extremely valuable. This diagram itself says a lot about how you can process long context data. Uh,
I
so
think you could do better. Because
really,
basically, yeah, they're just like, yeah, you could pass in multiple chunks. You could do a better long context rewrite. Like, this is not super efficient.
yeah, you're right.
But
It's not
also,
super
like,
efficient. Yeah,
yeah, it also depends on how long context documents you have, right? So,
maybe an
like, at
entire
a
book.
yeah. So, I mean, there's interesting stuff there. But the interesting note is the majority of the training was done at pretty short context, actually.
Exactly.
They
I was
talk
so
about this.
surprised. 4K context only. So, but okay, I'll let you get to that. I'll stop interrupting.
I mean, no, it makes sense, right? Like it's a trillion tokens. It's a trillion, sorry, trillion parameter. It's a big model. Like um that context really adds up. So they do context length extension later. I also just don't think that we have 15 trillion, like even trillions of tokens of really long context, right? Like that just doesn't exist. And it's so much more exponentially expensive to train at long context. Um, okay, so basically, they rewrite high quality math into learning note style. So instead of just question answers, here's a learning note of how I would solve this. translate high quality map into other languages. This is standard seen in other work as well. Okay, overall, they have 15 trillion tokens. I thought this was interesting. They have web text, code, math, and knowledge. I don't know what knowledge is, but they have knowledge. For each domain, we perform rigorous correctness and quality evals, standard filtration stuff. A lot of rewriting though. Okay, 32 billion active parameters, similar to DeepSeek V3. They use MLA. Um, as our attention mechanism, the hidden dimension of this. Okay, so scaling law analysis reveals that continued increase in sparsity yields substantial performance improvements, which motivated us to increase the number of experts to 384 instead of 256 in V3. To reduce computational overhead during inference, we cut the attention heads to 64 instead of 128. So they do scaling laws to reveal that based on the number of active parameters you want, increasing sparsity. So taking the same number of active parameters, but increasing total experts is better performance. And they they increase experts and they cut the attention heads in half. This helps with their training stability. So their new optimizer had issues and they cut attention heads in half. Okay, this is similar to DeepSeek. So more total parameters, less active parameters, more experts, less attention heads, only one dense layer, which they don't talk much about. Here's their sparsity scaling law. Sparse Oh, one sec. I'll be right back.
Oh no.
Oh no, does Mochi need to get out of the room? Or does Mochi need to get into the room?
Mochi has always his needs.
Mochi's FOMO from Paper Club. Oh, Mochi's here.
Oh, Mochi just needs papers. Mochi can chill with us. Sorry. Okay. Sparsity is the ratio of total experts compared to active experts. 48 is their magic number. But basically, what is this? They have 384 384 total experts and 16. Let's read through this. Okay, sparsity is a ratio of total number of experts compared to the number of active. So this is the scaling law basically that they find. Under a fixed number of active parameters, basically in this case, the 32B active parameters that they want to set, increasing the total number of experts, in basically making it more sparse, consistently lowers both the training and validation loss, thereby enhancing overall model performance. They do these experiments. Increasing sparsity leads to better performance. It also adds infrastructure complexity. There was a semi-analysis paper on like why Llama 4 failed, and they talk a lot about MOE stuff and their expert choice routing versus token choice routing and all these stability issues in infrastructure and how they and how they changed halfway through. But yeah, when you make stuff more sparse and you have like stuff like that, then you need to, you need to deal with infrastructure complexity. So they have a sparsity of 48, achieving activating 8 out of 384 experts per forward pass. Here's kind of their laws. So increased sparsity, better performance, doubling the number of attention heads. They also checked. It didn't take much of a hit. I think this is the next section. Frankie, you have hand up.
Yeah. I just wanted to ask maybe more of an interpretive kind of question here. So they found that increasing MOE is and decreasing number of heads, it's better. So could the interpretation be that the attention heads are essentially kind of like mixing stuff from your context? The MOEs is kind of figuring out what you do with that mix. So I think maybe it's saying that the expressivity of what you do with the mix is more important than the mixing itself. That is, you can kind of like get raw stuff from your neighbors, but you should be smarter about what you do with it. Would that be a correct interpretation? I know it's kind of hard, but what do you guys think?
Two things. So one, the attention head is not actually, it's not necessarily better to cut them, they did it for training stability. So the dots here are lower loss, but double the attention head. So more attention heads actually helps performance. It's just not much. Like they say, it's a doubling the number of attention heads led to a reduction in validation loss of 0.5 to 1.2%. So it's still better. It's not worse to have more attention heads. It's just a lot more it's a lot more complexity. So here's a cool quote. So with a sequence length of 128K, doubling the attention heads from 64 to 128 while keeping the total expert count fixed leads to an 83% increase in inference flops. So you're nearly doubling the compute required for inference by doubling your attention heads, but the performance increase is very small. And it had instability issues with their optimizer. This doesn't mean that Atom W with more attention heads isn't stable, but it's a big compute cost. So something to note there. Regarding the analogy, I think I need to hear it again. I don't know if someone else wants to comment, or maybe you want to post it in the chat, but I didn't really digest. And if someone else wants to comment, pop in.
I wanted to ask,
Actually,
is it more of the experts or the attention heads that we're, being optimized for here?
This is both. So they're keeping it sparse by having a lot of experts, but only a few active. That's one part of the equation. That's in their scaling laws, better performance. So if you have if you have a fixed inference budget, like let's say I want to run this thing at 32 billion active parameters, you'll do better by having more total experts. So that's part of it. That's for performance, right? That will get you better overall performance, even though it has training complexity. The attention heads is inference optimization. So, when you cut attention heads, you have less KVs, right? Each attention head basically has to do KVs, and over long sequences, KV is quadratic scaling, and that's a lot of GPU utilization. If you can cut half, you can kind of cut half of your KV cache, which is a lot of GPU usage. Eugene, it seems like you have good intuition. You wanna intuit?
No, I don't know if I have good intuition, but my thinking is that attention heads are just like an ensemble. And beyond a certain number, they found that, from 64 to 128, they say that, yes, while it does improve validation loss, like it's over there, only validation loss improved by 0.5% to 1.2%. And okay, given that fixed amount of compute, they rather not double, they rather halve the attention heads and have more experts. So it's a compute trade-off, which makes sense to me.
I think
No,
that
but
makes
go ahead.
sense. No, I think that makes sense. The difference here is also just the architecture, right? So we're operating on trillion parameter and 384 experts. Now, does this scale to dense models? Does this scale to a small 24B? Who knows? I think that's we'll have to figure that out, but it's verified in their case. I don't know if you can take this at face value for other architectures and other sizes. But I highlighted this in green. It's important. Very, very useful. Cutting attention heads saves a lot of compute at long context. But once again, attention is a problem at long context. This is like my one concern for like transformer alternatives and stuff. You guys really need to train at long context, right? Because the benefit of your like getting rid of attention and swapping it in with something like recurrent states, that's cool, but it really only makes a difference at long context. At short context, it's not that deep. And train at long context, even though you're not very GPU rich, do it anyway. Okay, training infrastructure. This was cool if you care about trade restriction. So basically, NVIDIA didn't allow H100, H200 exports, but China had the custom H800 GPU. This is their training node. So each node in the H800 cluster contains 2 terabytes of RAM and 8 GPUs connected with NVLink and NV switches within nodes. Across different nodes, 8 G8 400 gig ROCE interconnect. They talk about stuff with like PCIe offloading, saving to disk, weight optimization. So basically, the thing that Magistral did was really efficient to just keep rollouts 24/7. With this scale of trillion parameters, they did a lot more offloading to DRAM and stuff. Apparently, H200s are coming to China soon. Nvidia is winning. Actually, like there was a post about this where everyone was like, I don't know why DeepSeek had such a big impact on like Nvidia stock, because guess what? H800 is still Nvidia. Like it's all Nvidia at the end of the day. But ooh, Mochi trying to jump off table. Mochi, you stay. This is Mochi. Mochi's the non-expert doggo, but she's learning to be expert. Okay. Parallelism for model scaling. I don't know if we have that much time left for this, so maybe I go through this section quickly and we come back if we have time. I like this. I nerded out over this in the Magistral paper. Do the RL part. I think the RL and data gen stuff is more fun. Mochi, come here. Okay. I was gonna read a lot of this, but let's skip it for now. Basically, there's three things they do. Combination of 16-way pipeline parallelism, 16-way expert parallelism, and 0-1 data parallel. A lot of this is just like, if you're ever interested in how big models are trained, you should read this section. It's kind of cool. Here's what they have to go over: activation reduction, Swigglue, OKFP8 for more intensive outputs. What else? CPU offloading, training recipe. This was interesting. So training recipe. They mostly train at 4,000 token context window using their new optimizer. Total of 15 trillion tokens. The first 10 trillion tokens were, standard learning rate, small warm up. Then the last 5.5 trillion tokens, they had cosine decay, weight decay was set, global batch size was pretty large, 67 million tokens per batch. Crazy. Figure 4. Is there figure 4 that I skipped over? Da, 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 da. These figures were very odd. The rewrite takes both previous and the current segment. Okay, that's irrelevant right now. Okay, so most of the training was done at short context. Then towards the end, they had an annealing phase followed by long context activation stage. Batch size still 67 million tokens. Learning rate was decayed quite a bit more. In this phase, we trained 400 billion tokens with a 4K sequence length, followed by an additional 60 billion tokens on 32K sequence. Then they extend with yarn. So basically, 60 billion out of 15 trillion tokens are at 32K sequence. Very, very much like the majority of this training is just done at 4K context. Post-training, Muon is still used in post-training. If anyone's fine-tuning Kimi-K2, you should also still use this Muon optimizer. Don't use Atom W. It's cooked. I think there's a chance. So like one of the co-founders of XAI is Jimmy Ba, who worked on the Atom W optimizer. It's like his big thing. What are the odds that these people get poached to XAI because they like optimizers? Who else? Elon is trying to poach Karpathy again, but that's side T. Okay, SFT. So there's instruction tuning data set, maximizing probability of high response, data gen pipelines for different tasks and different domains. So they use Kimi-K1.5, their in-house domain specialized expert model, to generate candidate responses for various tasks, followed by LLM or human judges to perform automated query evaluation and filtering. For agentic data, we create a data synthesis pipeline to teach models tool use capabilities through multi-step interactive reading. This stuff is pretty interesting. This is like really the nice meat of this paper, I think. Okay, large scale agentic data synthesis for tool use. Basically, we need LLMs to be able to autonomously figure out how to use unfamiliar tools, interact with external environments, and iteratively refine their actions through reasoning, execution, and error correction. So here are some papers that you should check out about how to train tool use and tool use evaluation. So tool LM, ACE bench, and then same thing with synthetic data. So real world environments, Rich. So difficult to construct at scale, complexity, privacy, accessibility. Recent work on synthetic data gen, agent instruct, self-instruct, and stable tool bench and zero search. I think we covered agent instruct and self-instruct. Two new ones that they talk about here that if you're interested in synthetic data gen, you should probably check out. Stable tool bench and zero search. They show promise in creating large-scale data training without relying on real-world interactions. It's all synthetic. They have a pipeline that simulates real-world tool use scenarios at scale, enabling the generation of tens of thousands of diverse and high-quality training examples. Okay, 3 stages in data synthesis pipeline. Tool spec generation. So step 1 is, first construct a large repository of tools from both real world tools and LLM synthetic tools, agentic and task generation. For each tool sampled from the tool repository, so they have like thousands of tools, by the way, generate an agent to use a tool set and some corresponding tasks. Then trajectory generation for each agent and task, generate trajectories where the agent finishes a task by invoking tools. Here are some of those tools. So they have a bunch of real MCP tools. They kind of do a distinguish, they kind of like filter them out by category. So some search tools, database tools, communication, R&D. Then here's their synthetic tools. We'll go over this soon. First, we directly fetched 3,000 plus real MCP tools from GitHub repositories, leveraging existing high quality tool specs. The interesting thing with MCP tools is like, they don't really say how they verify that these are high quality tools, right? You can have non high quality MCPs. There's no like great standard over this, but they don't mention much filtration over this. Second, we systematically evolve synthetic tools through a hierarchical domain generation process. We begin with key categories. So they basically have like a categorizer that categorizes different tools in different domains. They start with that. So then we evolve multiple specific application domains with each category. Specialized tools are then synthesized for each domain with clear interfaces, descriptions, and operational semantics. So get a bunch of tools, classify them in categories, then evolve multiple specific application domains with each category. Then tools are synthesized. They produce over 20,000 synthetic tools across different domains. Both MCP and synthetic tools cover complementary regions. Okay, agent diversification. Seems like generating all these synthetic tool workflows would take a ton of compute. Yeah, there's a lot of inference that goes into this stuff. Okay, agent diversification. So we just casually generate thousands of distinct agents. They synthesize various system prompts and equip them with different combinations of tools from our repository. When I said that this is kind of basic, Eugene, this is kind of what I meant. Like, I didn't expect stuff like this to just work. Like, sure, you can get a bunch of tools, generate different categories and expand them out. I didn't expect diversity in these 20,000 tools, but this is what I really didn't understand. They just generate thousands of distinct agents with different combinations of tools from their repository. And, from this, they have rubrics of different stuff that they should be able to solve. And all this kind of just worked. They have varied capabilities, areas of expertise, behavior patterns, ensuring a broad range of potential use cases. And then before, this is the last section. For each agent config, we generate tasks that range from simple to complex operations. Each task is paired with an explicit rubric that specifies success criteria, expected tool use patterns. I don't know how they just generate tool use patterns, because if you can do inference to, figure out what are the tool uses, you kind of don't have the best quality data, right? Because like you can kind of solve the task, I guess. But like I get matching a task with tools, but not tool use pattern rubrics. And then evaluation checkpoints. Rubrics ensure consistent and objective evaluation of agentic performance. This is kind of interesting. Eugene, you wanna?
No, I get that. I think I think of this as like a huge synthetic data ETL pipeline. where you could be creating 100 traces, and through your quality evaluation and filtering, we don't know to what extent how strict they do it, but they could be filtering only to the best 10 or the best 5 even.
They talk about their filtration actually a bit. Like in some stuff, like in Magistral, they talked about like they get rid of stuff that Mistral Large could solve. They have something here that talks about
Yeah,
their
they have
filtration.
something here whereby they actually use an SFT model, and if the SFT model is only when the SFT model is not able to solve it, then they keep it. So it's really interesting, the data cleaning and data generation that they do.
Yeah, it's like it's cool. It's there. I think this paper could be a bit worded better, but it's still cool. It's still like nice that they explain all this. Okay, so multi-turn trajectory generation. They simulate real tool use scenarios, user simulation. So basically, LLMs are personas with communication styles. So like one might be moody, one might be authoritative, one might be stupid, one might be like PhD level smart. And preferences, they have multi-turn dialogues with agents, creating naturalistic interaction patterns. Tool execution environments. So there's a tool simulator. This is kind of cool. They talk about like their sandbox here. Um, a sophisticated tool simulator, functionally equivalent to a world model. They have AGI, I guess they have a world model. They execute tools and provide realistic feedback. Simulator maintains and updates state after each tool, enabling complex multi-step interactions. So this is like if you think of like Web Arena and stuff like that, where you kind of have like a fake website and you're shopping through. Instead, you have a simulator that might have like tasks, and as you interact and do stuff and use a tool, the simulator keeps state section by section. This is kind of cool. I wish they talked a bit more about this. It introduces controlled stochasticity to produce varied outcomes, including success, partial, and edge cases. So, you're actually changing an environment. A lot of this is like gym motivated style. But very cool. Like they have all of this. LLM-based judge evaluates trajectories against task rubrics. Only trajectories that meet success criteria are retained for training, ensuring high-quality data while only allowing natural variation in task completion. Interesting little section there. Yeah.
I'm sorry, jump the gun. I thought the hybrid approach, which is what you're going to talk about next, is amazingly cool because they fine-tune their judge on verifiable code, and then what they say is that from this verifiable code, the model is able to learn subjective eval. Actually, wait, am I looking at the right section? Sorry, guys, for this confusion.
Is this the section?
Yeah, I had a note somewhere. Give me a second. Let me check.
Okay.
Again.
I'm gonna cover this for now. So
yeah, go ahead.
There's inherent limitation to simulation fidelity. We complement our simulated environments with real execution sandbox. They talk about scraping a lot of like real GitHub issues. They want real authentic like stuff, right? So in coding and software engineering, they have execution sandbox. These execution sandbox execute actual code, interact with genuine development environments, and provide ground truth feedback for objective metrics and test suite pass rates. This allows them to learn from diversity of simulated scenarios and authenticity of real execution, significantly strengthening the practical agent capabilities. So in this hybrid pipeline, I don't think this is the section you're talking about, Eugene, but
you're right. Sorry, it's the section on closed loop. Yeah, we get to that when we get to that.
Okay, I think I'm gonna go a little fast because we're running short on time. But basically, rejection sampling. So get rid of the ones that are easy. Quality filtration. SFT has demonstrated improvements for tool use. Okay, RL. Better token efficiency than SFT. This is understood. They have a gym-like extensible framework that facilitates RL across a wide range of scenarios. Tasks with verifiable rewards. Subjective preferences such as creative writing, open-ended question answering. We introduce a self-critique reward in which models perform pairwise comparisons to judge its own outputs. It's like similar to GRPO, right? GRPO, you output a bunch of outputs and then you do preference over the group of outputs to what's the best. This instead is, you have a self-critique over your output and you judge your own output. So kind of interesting on how they do RL for creative writing and open-ended questions. verifiable rewards in gym. So I think we can skip some of this. For math and STEM, pretty straightforward. Complex instruction following. Is this what you're talking about, Eugene?
Oh no, it's
Hybrid.
slightly below.
Okay, okay.
We get it. Yeah.
Okay, so for hybrid rule verification, there's evaluation of code interpreters, LLM as a judge. Okay, multi-source instruction generation, complex prompts, faithfulness. This was kind of cool. They have this. There's this framework of facts grounding. There's a sentence level classifier judge that's prompted. That's useful to perform automated verification. Basically, it detects sentences that make factual claims without evidence and context. They have this as a bit of the reward in RL. So faithfulness, coding and software engineering. For
Again,
software,
this part is cool, right? In the sense that they rephrase the question, but they still care so much about factual verification, as well as the responses, factual verification. They are putting so much effort into this, as well as the coding, as well as they have adversarial prompts for their safety aspects as well. So it's very, very,
safety
very,
and faithfulness.
yeah, it's so interesting to see what are the key things. And there are some points where they say that the key challenge is faithfulness, reducing hallucinations, and scaling this. So essentially, they actually write very clearly, these are the challenges we are facing right now. If you read between the lines.
Yeah. This was cool. Basically, E2B style or Daytona style sandboxing. Very, very robust sandbox infrastructure. So PRs and issues from GitHub to build software development environments that consist of user prompt issues and executable unit tests. So real GitHub stuff has unit tests. This environment was built on a robust sandbox infrastructure powered by Kubernetes for scalability and security. It supports over 10,000 concurrent sandbox instances while with stable performance. They just cranked that out real quick. Safety, they have attack model that generates adversarial prompts, a target model that produces responses, and then a judge that determines if they could bypass the safety mechanism. Each iteration is assessed with a rubric and then it's used in the reward. 10K concurrent agents, crazy, right? Okay, beyond verification, self-critique rubric reward. So self-critique rubric reward is what they did. General RL with self-critique, it evaluates its own outputs to generate preference signals. It initializes critiquability in the SFT stage. Since we're kind of out of time, I'm gonna really, really quickly do the rest of this and then we'll stay for discussion. But I guess if anyone has any questions, I guess now's your chance if you have to hop. Or if Eugene, you want to add in.
Maybe I'll just focus on the last paragraph in page 12 here. If you read this right, the critic model is refined with verifiable signals. So they fine-tune the critic model with the verifiable signals. They continuously update this critique. This transfer learning process grounds. So this transfers subjective judgments, allowing the performance gains from verifiable tasks to enhance the critic's judgment on complex tasks that like explicit reward. That's crazy in the sense that you can fine-tune, essentially you can bootstrap yourself on verifiable reward to train a reward model for non-verifiable reward. How that transfers, I don't know. I don't know what the intuition is on that, but I think there's a lot in this paragraph here on reward modeling and evaluation.
Yeah, the critique just keeps getting better and better, right? They update the critiques as well, and it recalibrates its evaluation standards and locks up a policy evaluation.
So if you look at this, right now we are solving verifiable reward like code and software, right? And the question we always have, would this generalize to non-verifiable reward? I think this paragraph here says that maybe it would, in the sense that at least non-verifiable reward is helping non-verifiable reward evaluation. So we start from there.
Very interesting. RL has slight modification policy, so they have their muon optimizer, several additions, budget control. So they say properly distributed inference budget we enforce. So they kind of shit on reasoning models. RL often results in substantial increase in length model generated outputs. Now, even though that gives improvement in performance, these benefits often do not justify its inference costs in non-reasoning domains. So for general stuff, you don't want this. To encourage the model to properly distribute its inference budget, we enforce a per sample maximum token budget throughout RL training. And the budget is determined based on the type of task. So hard task, you can reason a little more. Responses that exceed this token budget are truncated and assigned a penalty. This is all done in the formula there. Ochi, come here. It incentivizes the model to generate solutions within the limit, enhances its token efficiency to get concise and effective solutions. PTX loss, this just keeps it grounded in previous stuff. Temperature decay, when it starts out, you want high temperature so it can explore different stuff. Then you tone it down. RL infrastructure, I don't think we have time for a lot of this. Efficient engine swapping, efficient system startup, agentic rollout. RL infrastructure supports training on long horizon, multi-turn agentic tasks. Tasks present distinct challenges. Two strategies deploy heavy environments. Okay, evals, it books. All the evals are done at 4K context. Yeah, soda, berry soda. I think that's enough. Red teaming, they do some red teaming here. Limitations. When dealing with hard reasoning tasks or unclear tool definition, the model may generate excessive tokens, sometimes leading to truncated outputs or incomplete tool calls. Basically, they have it in their RL that if it's too long, we just truncate and it's cooked. That can lead to it wasting its context and then cutting off at tool calls. Additionally, performance may decline on certain tasks if tool use is unnecessarily enabled. When building a complete software project, the success rate of one-shot prompting is not as good as K2 and their agentic coding stuff. Yeah, that's paper. Sorry. Anyone familiar with the RL formula? What RL variant is it based on? Let me check. I thought I knew this.
I think they said it's based
Or-
on the Kimi V1.5. I haven't had a chance to go through that.
Okay,
Yeah,
well,
it is a
we'll
Kimi 1.5.
What is
But what is the Kimi
1.5?
1.5 based on?
It's the same. The reward model. So the reward model minus the mean R. So you can go back to
So
the equation.
GRPO.
Yes, it has GRPO in it, but it doesn't go through the partial sequence, right? So GRPO actually goes through partial sequence, and
I
this
see.
one doesn't, just a final.
Okay, thank you.
It looked GRPO-esque. Any other thoughts, questions, comments?
So I was wondering, like for the 10,000 agents, it seems like a bit excessive because is it the fact that all these agents are doing something a little bit different? Like how does
Do you
it take?
mean
Yeah.
do you mean the sandbox execution?
No, given that you have so many tools, right?
No, it's
So
10,000 concurrent sandboxes,
oh, okay, I'm sorry.
which I extrapolated
Yeah.
to 10,000 agents running. It may be the same agent, maybe the same
I
code.
think I think this is just like when you're training in batch size of like 67 million or whatever, you need a way to run your verification and stuff, right? And you need to be able to let this thing call tools and like so when you're doing rollouts, you're testing how well it can use tools and interact with the environment. And you have to keep state for these environments. Now, you need a bunch of environments running. So this is like, this is for that. It's not 10,000 agents like
So
swarming out to solve stuff.
maybe more like figure 9, right? Which each dot is like a different tool. Is that correct? So basically the synthetic tool, right? Yeah, you just had it right there with a bunch of colors. Yeah, right
It's
there.
figure 8.
So
Yeah,
yeah, figure 9, right?
nine,
So figure
nine.
9, they create a lot of synthetic tools, and I was wondering, like, does that diversity really help out that much of different tools? Like, are some of these doing redundant stuff? So that's my question.
Yes, they're definitely doing redundant stuff, right? Because I mean, how many categories do you have here? You have 10,000 tools, and how many colors do we see? I see maybe 30, 40 colors. So yes, tools are doing similar categories of stuff, but it's still like even if you have a tool in the same category, as long as it has different descriptions, different ways to use it, different steps, because they don't just look at, like, their rubric isn't only on full task completion. So they have, like, in the middle checks for, you know, partial completion, as long as it's using the right tool use, like the right steps. That's still a good output. But I think their sandbox is basically just keeping their environment online and, like, allowing these tool calls and these different environments to just keep state.
I guess my question is like, do they want to specifically add so much redundancy because you want the model to better generalize to usage? Because if I was kind of like have this diversity of stuff which does similar things, how do I know which tool to even pick, right? So I'm trying to understand like what's the reasoning for
They're
that. Yeah.
they're predetermined. So in their data gen pipeline, they create agents that have specified what tools they're allowed to use. So I think one, yes, you want diversity and being able to generalize and use different tools. But two, when they generate the agents themselves, they're given
Okay, got you.
different.
Yeah, makes sense.
Yeah.
Yeah,
I'll
I
try to
understand you.
find the quote.
Yeah, you're saying that they only present a certain number of tools, right?
Mhm.
So that makes sense.
They're not given
Thanks.
everything. Yeah.
Got you.
So basically, we generate thousands of distinct agents by synthesizing various system prompts and equipping them with different combinations of tools from our repository. So it's not like they have access to all 10,000. You probably have an agent that does something that has access to like 4 tools with varied capabilities, areas of expertise, and behavioral patterns.
I know Amgad has a hand raised.
Yeah, thanks a lot for the amazing walkthrough. I just wanted to go back to the point about whether this is a reasoning or non-reasoning model. I think this one is non-reasoning because one of the reasons I have a gripe with the recent reasoning models is they take too long to give you the answer. And there is like an argument about whether we can justify this increase in cost and latency, like whether the increase in performance can justify the increase in cost and latency. But for this model, if you ask it to translate a document from English to French, it will give you the French translation right away. It will not think for 500 or 1,000 tokens.
I think that's part of it. The other approach there is hybrid reasoning and non-reasoning models, right? Like you can turn on and off reasoning. So like Claude models have thinking and non-thinking modes. Small LM3 is a specific like recipe to train a hybrid reasoning model. Basically in that in their RL stage with GRPO, they mix in stuff that's a subset of reasoning and non-reasoning, and they reward them equally. But I do agree. Like I really think that like they're kind of pushing the cost onto you, right? Like for basic stuff, I don't want to pay extra tokens. And the proper like the proper gauge for models right now is no longer price to um like before it used to be price to intelligence ratio, right? So how much do I pay for this level of intelligence? It's very skewed now, right? A model can have an intelligence that's very high, but it could take twice the cost in the terms of number of tokens to get there. The number of tokens to get that intelligence is kind of variable. What would be interesting now, I think, is in some benchmarks, if we could include how many tokens were used in reasoning for specific like questions or stuff. I don't know a great way to measure this. I haven't really thought about it too much, but you know what I mean? Like cost to performance is no longer as relevant because your performance has variable number of thinking for different like models. Like some models are very verbose in their thinking. The DeepSeek update basically got it for think for twice as long, which could also mean to, you know, charge you twice as much. But on the other hand, like it's a significant performance increase, right? So like, are you really gonna make that trade-off? I think in general, even though it was forced on people, like O1 was the first reasoning model and you didn't have a choice, right? It's not hybrid. Like if you want reasoning, you're gonna use full reasoning. And people were fine waiting an extra minute for performance and the costs always come down. But that's just high level thinking in my opinion. I haven't given it much more thought.
Yeah, that's a good argument about cost.
Yeah. Any other thoughts, comments, questions, anything I missed in this paper? Sorry, I like yapped too much in the beginning. I didn't realize it would take so long. I was gonna think it was a quick one.
It's quite a dense paper, like lots of stuff to go through.
Yeah, I think their like muon clip stuff is pretty interesting, but like there's only a few takeaways, right? Like they do some cool scaling laws. Basically, they do like individual attention head level parameter clipping of optimization, and that leads to really cool scaling. The bigger takeaway of this is like it's very, very expensive for labs to do big train runs. And like loss spikes are a big detriment because basically, if something gets cooked, like all your major infrastructure is being useless, and you might have to roll back and restart and rechange weights and load weights. And like that's a huge delay in a lot of GPUs. So stability in training is like quite huge. But that's like the big takeaway. And then check out last week's paper. You know, we kind of dove into the optimizer. Frankie, you have hand up?
Yeah, I think just with the comment from Eugene on that paragraph on self-critique closed loop. So I'm wondering, like, because again, like, how does it learn from giving subjective rewards, right? So I'm wondering, does it have to do with the fact that they're critiquing on the verifiable signals, right? So there's things that are definitely verifiable, but because you have things which are not verifiable, do you think that the model is kind of like learning from the steps that were taken, right? It's kind of like the chain of thought or whatever, if you like, learning from the steps. Like if it looks like you're doing good steps, then I can reward you better. So because you don't have you have a subjective reward only, right? So just wanted to see how you guys thought about that.
Yeah, kind of. In their rubric, they have rubrics that are for like potential steps. So given this, like, let me try to find it. Given this prompt or question and these set of tools, here, I think this is it. Combine RLVR with the self-critique rubric reward. The model learns not only from externally defined tasks, but also from evaluating its own inputs, extending alignment from now. Basically, in the rubric, if you're using the right tools and getting like the right steps, you're rewarded for that too. But I think we can do a bit of a follow-up on this. For each agent, we generate tasks that range from simple to complex. Each task is paired with an explicit rubric that specifies the success criteria, expected tool use, and evaluation checkpoints. This rubric-based approach ensures consistent objective evaluation of agent performance. Where else is this mentioned? Expert crafted conditional prompts and rubrics developed by our data team. Oh, this is kind of interesting how they developed this. Agentic instruction augmentation, fine tuning. Okay, each iteration is assessed using task specific rubric, enabling the judge model to provide binary success failures. That's for success. Beyond verification, self-critique. Self-critique reward will evaluate its outputs. Initial critique is ability in SFT stage. Eliminate reward hacking. Clarity, relevance. So this is some of it. Core rubrics for RL. Clarity and relevance. Assess the extent to which the response. So this is the rubric used in the RL for the rollout. Assess the extent to which the response is succinct with full addressing the user's intent. The focus on eliminating unnecessary details, staying aligned, central with the query. Efficient formats such as brief paragraphs or compact lists. Conversation fluency, engagement, it's coherent. So, basically, yeah, they have an RL reward for stuff like clarity, conciseness, staying on topic, objective groundedness, like are you objectively answering the question, perspectives. So,
So you think that this rubrics is kind of help it to like decide what's good or bad? Is that what you're saying?
yeah, in the group of outputs, because it's based on GRPO, right? You're still giving a reward for it. Like you're now not verifying. Well, yeah, in a sense you are verifying, right? Because in a group of rollouts, you're giving reward to the ones that match these, right? So you give a reward for stuff that's clear, give a reward for stuff that's fluent, give a reward for stuff that's objective, has justification, and you're explicitly adding that in your RL policy. So it's not verifying on stuff like, okay, end output is like verified and boxed math answer or code that compiles. You do have a rubric that verifies for this. I think the interesting thing is that they have a policy model that iteratively learns better critiquing and can self-critique. That makes this possible. Because otherwise it's like, okay, yeah, this is essentially just an LLM as a judge as your RL on output. And we know that RL is very, very, what's the term I'm looking for? It's, it has to, it's like very, damn, I'm blanking on the word. Fuck, I blanked on the word, but it has to be concise, right? Like you can't have noise in your RL policy, otherwise you won't generalize. There's a term for this that I'm blanking on, and you would assume that just having a basic LLM as a judge for your output for non-verifiable stuff, like is this good? Is this concise? Wouldn't work. But this kind of shows that if you keep your verifiable trained, ooh, Sochi, come here. Okay. Yes. Read this section.
Thanks. But what is your what makes you think that it is kind of improving its critique capability as it progresses?
It says it.
Oh, yeah.
It says it in one of those sections.
Okay.
That section that Eugene highlighted is
Yeah.
literally about keeping it improving. Where is it?
The
Yeah.
is a closed loop one, right?
Yeah, the closed loop thing. So yeah, that's how I
Yeah,
know. It's
yeah, okay. Thanks.
cool. Any other stuff? Yeah, closed loop. Our critique model is refined using verifiable signals. On policy rollouts generated from verifiable rewards continuously update the critic, a crucial step that distills objective performance signals from RLVR directly. They even talk about this in the infrastructure section about loading, moving these weights and stuff. This closed loop process ensures that the critique continuously recalibrates its evaluation standards in lockstep with policy evaluation. So this is like what Eugene was saying, right? This closed loop stuff lets you do RL on verifiable rewards. Basically, you have a good rubric and you iteratively get better.
Thank you.
Cool, guys. We're 20 minutes over, so I think that's where I call it. If anyone wants to volunteer for next week, that would be sick. Find a cool paper. We share a bunch of papers in Discord. I have like 4 or 5 that I'd recommend. But if anyone wants to present, would be sick. I think Swix, you're speaking but muted. All right, next week, guys. I'll see you.